Okay, so okay, sorry for this delayed start of our lecture 13. Okay, so have you done your homework program? So lecture homework 12. You all uploaded your PDF file?
Yeah.
Okay. So I see that it's not that difficult to you because all information is available to you. So let's come back to the review of our previous lecture, lecture 12. So please note that we are now talking about a certain node, and there we can find multiple triangles connected to this node. Okay, you can always find such kind of triangle. Then in this case we have to find out something like this. So starting from midpoint of this triangle edge, then of course we can find this circumcenter. This is circumcenter of this triangle, and the distance from this circumcenter to our three vertices, that is equal to, so the same for all three vertices. And in this case we have to find out the flux between these two nodes and these two nodes. So so direction is really arbitrary. So for example we can say this is the direction and this is the direction. So no one can say that this yellow one should be preferred than black one. So in some sense, for example, when we consider this node as a center node, then maybe this yellow color seems to be okay. But if we are considering, for example, this other vertex as a center node, then maybe this yellow colored direction is not that much appropriate. So point is, there is no preferred way between two vertices. So please try to evaluate this vector only once. Yes, this vector can be generated only once, and from the viewpoint of this center node, that should be regarded as positive or outgoing flux, and from the viewpoint of this vertex, that should be regarded as incoming one, so contributing to a negative wave for this integrated divergence. So only calculate it once and use it twice. So because there are two center nodes corresponding to this one single edge, so you can do it in that way. Of course, here you have this area, although this is just length, but always keep in mind that we have the hidden third direction, W direction, so we will multiply that W to our area or our length, so that will generate an area. So yes, depending on that number, we can just scale this flux. Yeah. So that was the first part of our previous lecture, and now we can restrict just these two cases. Here we have xi and xj, and we want to evaluate the flux between these two nodes. So once again, since this concept is quite confusing to newcomers, I wanted to repeat once again. So sometimes students say that how can I set xi and xj? So this should be xi or this should be xi. So as I told you before, there is no preferred way to setting which one is the I node and which one is the j node. That is really arbitrary. So you can just follow your own way, but when you consider certain node, then that flux should be counted with the correct sign. So if you set this is your default direction for your j sub n, then for this node, this contribution will be positive, and for same flux, that will contribute exactly same magnitude but negative sign. So that is quite obvious, but sometimes new students are confused with this concept, so they always ask me, how can I set that I node and j node? So please, that is really up to you, but one thing we have to keep in mind is, although that is depending on your choice, but final matrix which is calculated from your construction, Jacobian construction, should be identical. Although you take this direction and other student takes this direction, but when we compare two Jacobian matrices generated by one student and other students, they should be the same. So that is one thing I wanted to repeatedly emphasize, because I have seen that many students are confused with this concept so frequently. So now, if we restrict it to just one-dimensional approximation, and I told you that this is just one approximation, we have discussed about certain Manhattan structure, so structure like just made of several rectangles, and find that if the flux is really physically given by this direction. So this diagonal flux cannot be well described by this Manhattan style mesh. So if we really wanted to discretize it with our rectangular mesh, then maybe that will be the better way to discretize the system. If we introduce such kind of a mesh system, then our flux is really well aligned with this edge, and you will find that there is actually no flux between these two vertices, and we have a strong current conduction through this edge. So yes, that looks great, but before solving the system, actually it is a little difficult to predefine the direction of current. The current is obtained from the extensive simulation, so we cannot predefine that will be the direction of our current conduction. Of course, from accumulated experience, for example, if we are talking about MOS field effect transistor, then maybe the current direction will just look like this. So maybe it is good to introduce some vertices which are aligned, this is horizontal line. But even in this case, if we are going to, for example, very close to the drain end of our channel, then as you may remember, so there is a current spreading effect. So here, if we are going to the saturation region, then there is no inversion charge. So the current electrons existing here should move in that way. So they are spread and just drained in this drain contact. Yes, this is drain. So I'm not quite sure you have studied this one is in your undergraduate level, but anyway, important thing is even in this MOSFET, which seems to be quite unidirectional, but even in this case we cannot predefine the best mesh for our MOSFET simulation, so it's not possible. Of course, the pioneers in this field, computational microelectronics, worried about that situation, so they try to introduce a certain capability like adaptive mesh. So even for commercial device simulators, we can find this capability. Means that once solve the system with predefined mesh system, and once we have performed the simulation, then now we can find approximate result for our current density. After that, they try to just remesh the semiconductor device in order to have a better resolution about current density or electron density, electric field, any kind of a component. Of course, since depending on the bias condition, the current density or electron density can drastically change it. So their mesh for certain bias condition can be adaptively changed. So there is some capability called adaptive mesh. But frankly speaking, even when I work with some companies, so usually they don't want to introduce adaptive mesh. It is because at least that introduces a huge computational burden. So that in everyday life, TCAD simulation should be done in a short time. So otherwise, your engineers cannot wait for forever. So if you have to really want to have a good mesh, usual approach is not turning on this adaptive mesh capability. Instead of that, they just try to build a better mesh which is more or less suitable for all bias conditions considered in their simulation domain. So that is the usual way. So usually they just make a mesh. Oh, and if they have certain problems like accuracy problem or stability problem, it means that convergence problem, then they find that my mesh is too crude and too coarse, and just to find out some points where problems occur, then try to remesh those localized points again. Then maybe in many cases it improves the accuracy and also in the stability. Of course, there will be the degradation of numerical efficiency. Your simulation will take longer time than before, of course, but anyway, they just manage to find out a better mesh in this incremental way. So although adaptive mesh is available to commercial ticket simulators, but usually it is not much widely used. So I will not talk about this one. So, but please keep in mind that all of our discussion is based upon the assumption that we have a reasonably fine mesh for our system. That should be guaranteed. So developer cannot guarantee that point. So the user, so clever user, should build a good enough mesh, sufficiently good mesh for their own interest. Okay, so then now let's go to this one-dimensional approximation. So I think that I have sufficiently explained about some quotients before starting this fully one-dimensional approximation. And now I hope that you have already done the Schapter-Human scheme. So in our textbook, so we have spent quite many exercises to emphasize the poor performance of naive discretization approach. So that was because for user students it will be very difficult to convince them why we have to introduce such kind of complicated discretization scheme. But I think that to all three of you, we don't have to explain further about the importance of a Schapter-Human scheme. So please just accept its importance. Then let me just directly write down the form. So Jn, this is now one-dimensional quantity. So instead of just vector notation, I will use one-dimensional scalar notation. But please note that this is Jn vector, in this case corresponding to Jn times x directional unit vector. So you know it. So in this case we can say q mu n and d phi over dx, and q dn dx. So after long discussion, you will have the form of what? Form of a Schapter-Human scheme, discretization. Then how can you remember that one? So I assume that you all understand the derivation. So it is just understood, and that is most important. But once you understand that important derivation procedure, then you have to use it. So usually the form is given by this way. So first of all, q mu n. So now you can just pull this number and you will have this one, and also have vt times dn over dx. Once we have this form, well, what was the assumption? So here we have introduced vt. So combination or product between this mu n and summer voltage will give us diffusivity dn. So as you may know, this is an assumption, and this assumption actually exactly valid at equilibrium. So at equilibrium, so we have the relation called Einstein relation. So dn, diffusivity, is simply given by Vt times mu n. So this is not an approximation, this is really valid relation. But if we go to non-equilibrium case, then there is no guarantee that dn and Vt times mu n should be the same. Of course they can, but sometimes they may not be the same. So the point is, although this relation dn equal to Vt times mu n is not strictly valid at non-equilibrium case, but we just impose this condition. So at first glance you feel that that's good, okay, I will just accept it because that is widely used. But you know that this assumption has been the root cause of many transport models in the semiconductor industry, because once we accept this one, then we are restricting ourselves to the situation which is quite close to equilibrium. This assumption means that although we are working with a nonlinear non-equilibrium case, but the deviation from the equilibrium case is not that much significant. That is the assumption, implicit assumption we have to understand when you use this Einstein relation. But you know that what is the actual application bias for our drift diffusion model? We are applying our drift diffusion model to not only small drain bias case, but we are also applying it to, for example, saturation, whatever. So we are really applying to everywhere. So even the case this Einstein relation does not hold any longer. So that is the limitation, or one of the limitation of this drift diffusion model. But anyway, once we accept this one, then you can find the result. But I wanted to tell you how can I remember this one. So maybe you can find that there is something is positive, something is negative, and Bernoulli function. So you can find that is quite difficult to memorize it. So my trick is disclosed now. So here, of course, this is a drift diffusion model. So for some cases, drift can be dominant, and for some cases, the diffusion can be dominant. But our scheme should be valid for both cases. So please remember this one. So I just wanted to ask you, consider the the extreme case where we have almost no drift term. So if we have diffusion dominant form of our expression, then what will happen? Of course, then it can be approximated as here minus Vt and dn over dx. So please, here I made the dominance of diffusion term. So I just neglected the drift term here. So of course it cannot be an exact expression. So this is only valid under the approximated condition. So let me just write down Qn. Here we have Vt, so they are just minus. We have this form. Yes, that is really simple. And if you have to discretize this form, what will be your choice? So your choice will be obviously q mu n vt. Then you will introduce this one, xj minus xi. So xi and xj are aligned in this way. Then here, since we have to introduce something like dn over dx, so here we have to nj minus ni. So are you all with me? So then let me just write down. So if we adopt this diffusion dominant form of our drift diffusion equation, that things gets really simplified, and you know that, then we can write down Jn under the assumption of dominance of dominance of diffusion current. Then we can say Q mu n Vt and 1 over the position difference, okay, or the length of our edge, interested edge. Then we will have eventually nj minus ni. So that will be the discretized form of your current density. So of course this is good for the case where the drift term is negligible. However, we have to generalize it. So how can we generalize this form? So my trick to remember this one is, now we have here coefficient 1 and here we have coefficient 1, and that can be generalized. So please remember that what was your Shapeter-Gumel scheme form? That contains a so-called Bernoulli function, and Bernoulli function is something like this. So it has the the index or input argument like phi j minus phi I. That is used for input argument of your Bernoulli function. So I wanted to say that here we can introduce certain Bernoulli function, and here we can also introduce certain Bernoulli function. Yes, something. Yes, so we can think about this form. Okay, so do you have any question up to now? So my suggestion is, okay, but please note that today's lecture, currently I'm talking about the way for remembering this Bernoulli function or Shapeter-Gumel scheme. But more important thing is the previous homework number 12. So, and in any cases, if you have a sufficient time, you should be able to derive the Shapeter-Gumel scheme by yourself. I just believe that you can do it by yourself, all three students. So that's the reason why now I'm just talking about how can we so say this is how can we have how can we remember this one. So trick is like this. So just to remember the form for your diffusion dominant flux. After that, this coefficient in the case of a diffusion dominant case, this coefficient is 1 and this coefficient is also 1. However, when you remember the Bernoulli function, so if this is your input argument of a Bernoulli function, and if this is its function value, then you can find that if we have 0 value, then what will be the function value? That will be 1. And here we have a slope corresponding to slope equal to minus half, and yes, and we have exponential decay. Here we have exponential decaying function, and here we have some asymptotic form like this. Yes, it just to try to follow that green line, and that green line is given by simply given by Bernoulli function of chi should follow minus chi. So that is one thing. So simply speaking, yes, the chi function here is regarded as voltage difference divided by summer voltage. And if we have really diffusion dominant case, it means that we have no potential difference between two nodes. So simply speaking, this point is corresponding to your diffusion dominant case. And if you have a really diffusion dominant case, your function value is 1, so your Bernoulli function will give, both of them will give 1 and 1, so that is perfectly fit for your application. And if we introduce now here chi and minus chi, so here chi is defined as this way, so potential difference divided by summer voltage. So if we have this form, then if now let's say that V phi j is much larger than phi I. If we have this form, then chi itself will be much larger than 0. So think about this extreme. Then what will happen? When chi is much larger than 0, simply speaking, this first term related with this b of chi will just diminish it. And after that, also this one will survive. So if I write down certain case where chi is much larger than 0, then I can certainly say that in this case it is now approaching to q mu m b t, so all kinds of leading coefficient, and now we will have here n I. Oh, sorry about that. So my pencil is lost. Okay. Oh. Okay, now it works again. Something is not very good for my pencil. Pencil is okay, but how can I delete it? Yes. Yes. No. No. Okay. But anyway, let's just come back to our usual way. Here, please neglect this ugly line. So here we have n I, and just chi will occur. Why? Because Bernoulli function of minus chi will approach to what? To just chi. So you know that since Bernoulli of chi will approach to minus chi, so yes, if we insert this number, obviously we will have just positive. Then we will, here this one will approach to chi, so here we have a negative sign, so I have to say here once again negative sign. Then let me just finally collect all of these informations. Then it will approach to what? Q mu n v t 1 over x j minus x I and minus n I. And what is chi? Chi is defined as phi j minus phi I divided by vt. So you know that this vt and other vt, they can be cancelled out, and here you have finally here you have minus and delta x and delta phi. What is it? So minus delta phi divided by delta x, that is corresponding to your electric field, the x directional electric field. And finally you will get the form like this: q mu n and your ni and your approximate expression for your electric field E. So E here, when I write down once again, that should be written as minus phi j minus phi I xj minus xi. So I'm just showing you that if we assume this kind of form, n minus n form, then it is approaching to both of drift dominant form and diffusion dominant form correctly. So please try to remember your Bernoulli function based upon this diffusion dominant form, and just to modify your previous coefficient 1 and 1 with proper value of Bernoulli function. So maybe then you can ask me one further question. Okay, it sounds great, but how can I determine the sign of our Bernoulli function? Which one should be positive and which one should be negative? Oh, that should be remembered by yourself. So there is so please remember that this one should take a positive and this one takes negative, and chi is defined by just a difference from phi j minus phi I. Okay? Then let's come back. If we go to instead of jn, just let me apply my full approximation like this. Then how can we write down the form of jp? If we just write down the diffusion dominant form, then do you remember the coefficient for diffusion term in whole current density? In this case we have to have a minus sign. So here we have dt and 1 over xj minus xi. So also we introduce pj and pi. Yes, now we can introduce certain Bernoulli function and certain Bernoulli function. And let's assume that we introduce the same argument like this. Then what will happen? If we adopt this form, then obviously once again when we have a positive chi, this one will survive just like a jn. Then we will have the opposite sign for our drift component, because here we have overall sign difference in this part. So diffusion term generated from this Schapper-Gummel scheme will have the opposite sign. But if you remember correctly, the drift term of Jn or drift term of Jp, so if we have drift and if we have drift, and they look like, both of them just to look like Qn E and also Q U P P E. They have the same sign. So if we just introduce such kind of construction, then it is just introduce a long way. So the way to remedy this problem is simply introduce here negative sign and here positive sign. That will solve everything, because in this case this guy will survive, and that will introduce different sign. Once again another negative sign comes in, so we will have overall the same values for both of Jn drift term and Jp drift term. So simply speaking, then I have to first close this application once again, because my ugly drawing comes in and comes out. So Simply speaking, up to now, I have explained how can you memorize the form of your Shapiro-Gumel scheme, both for electrons and holes, and it was quite easy. It means that just to introduce or just to write down your diffusion dominant term and just to consider the generalized coefficient instead of just number one. You can introduce the Bernoulli function. Of course, the input argument should be the potential difference normalized by the thermal voltage. However, in this case, you can select positive or negative value, and that value should be carefully inserted to have correct limiting factor. However, frankly speaking, I just remember that sign. So in the case of electrons, yes, I just remember this one, J and positive minus Ni Bernoulli. Yes, that is the thing I remember. Also, I remember instead of remember this whole, I do not explicitly remember the form for holes, but instead of that, I just remember that the input argument for our Bernoulli function should be inverted. So inverted for our whole current density. So that's it for remembering all these complicated notations. Okay, do you have any question about the lecture contents? So I once again wanted to emphasize that this is just my simple trick to quickly remember the result. But point is, before understanding this trick, you should derive the Shapiro-Gumel discretization by yourself. This is the most important. I think that is the single most thing you have to have in this semester. If you don't remember anything in this semester, but you just to select the only thing you have to remember, you can bring to your home, then I think that derivation of Shapiro-Gumel scheme is the thing you have to remember. Okay, so then I think that now the next goal is quite clear. So previously you did your homework for a system like solving Poisson equation and expression for electrons and expression for holes. Yes, that is strictly valid at equilibrium case. But now you have the Shapiro-Gumel scheme. So obviously the next goal is first solve this system. Yes, then as a result you will have phi and p as solution variables. Then with this one, now you can apply your solution to now different set of equations, electron continuity and hole continuity. So you can apply this solution as an initial guess for a new set of coupled equations. And obviously at equilibrium, since this is already a solution, then when you just evaluate it, then you will find that okay, my Poisson equation gives really negligible residue vector. Okay, and even when I apply or when I evaluate the electron continuity and hole continuity, I found that the residual vector out of the continuity equations are quite close to a null vector. So yes, so simply speaking, when you say Ax equal to B, since our temporal or approximate solution is the solution. So we will have a vector b which is quite close to 0. So when you just solve the set of this equation, of course you will get x. But since b is close to 0, so your x will be, of course, close to quite 0. So what will happen? So the expected behavior is once you insert your solution, equilibrium solution, into this new set of equations, and you will find this way. Oh, my residue is so small. So my solution, update vector is so small. So our criterion for convergence is automatically satisfied at the first Newton iterations. So you will have just a trivial first round. Okay, so that is one thing. The first thing you have to check. I simply think means that please solve the drift diffusion model at equilibrium condition first. But in this case, do not start from the crude solution, but instead start from the exact solution you have obtained from different set. So this is nonlinear, not exactly nonlinear Poisson equation, but this is equivalent to the nonlinear Poisson equation. So you have the solution of this system, and when you just apply that solution to a new set drift diffusion model, you will get immediately the solution. So if you say, when I solve it, then my Newton iteration takes 3 or 4 Newton iterations. Is it enough or not? So I want to say that no, it's not. So it means that it really should give us only one single Newton iterations. So when you just evaluate it, due to the how can I say, numerical error, your residue vector cannot be exactly a null vector. Of course, there will be a small number. However, the small number is really small, so you will have just negligible update vector, and that will automatically guarantee the convergence of your first Newton iteration. So if your solution gives you multiple iterations for your DD system, that simply means that there is something wrong. Which one is wrong? I don't know. If your nonlinear Poisson equation is wrong, that can happen. Or if your drift diffusion is wrong, also that can happen. Or both of them are wrong, yes, that can happen. So please note that once you build your system quite reasonably for both of the nonlinear Poisson-like system and drift diffusion system, then you will have a really negligible number of iteration. After that, now you have the drift diffusion model which is working at equilibrium case. Then what will be the next part? Of course, the next part is just bias lagging. So I wanted to ask you several tasks for your drift diffusion model. So please introduce the double gate model. I guess that all of you are working with the double gate model we have introduced in the textbook. So for that model, please test several scenarios like this. So starting from your VG and VD, and of course you are 0 and 0. Yes, great. Now you have a working drift diffusion core at equilibrium. So first scenario goes like this. Of course, this is the fundamental one. Please note that this is really the fundamental one. the most important one is just to increase your the pair of BG and BD into 0,1 milli. Okay, so simply speaking, just to increase your drain bias only up to 1 millivolt. So quite close to your equilibrium case. After that, just to keep your drain voltage as 1 millivolt, 10 to the minus 3 volt, and just to increase this number to certain voltage. What was the voltage you have tested for this system? I guess that it's about 0.7 over 1 volt. So please, let's try for 1 volt. Increase the gate bias only 1 volt, and after that, please draw a curve like this. Yes, now you have gate bias and you have drain current. So of course here we have other other two current components like gate current and source current. However, since we are working with the DC condition, yes, there is no gate current at all, and this source current should be identically the same with our drain current. Only the sign should be the opposite. So although we have three different terminal currents in general, but in this case only ID is the meaningful value. So you can draw this ID versus VG curve. So once again, I want to emphasize that this is fundamental for every simulation, transistor MOSFET simulation. When you do such kind of thing, always try to keep your drain bias really a low value, quite small, like 1 millivolt or sometimes 10 millivolt. Yes, it's okay. After that, just to run the simulation. So then you will have certain behavior like this. Then when you have this one, then you can easily find out the most important quantity of the transistor. What is it? The most important parameter is so okay, so current value is also important, but before doing that we have to find out the threshold voltage. So because we are using our transistors as switches, so threshold voltage just to represent the voltage where our device finally turned on and turned off. So that will be the border between turned off device and turned on device. So this is fundamentally important, and you have to find out the threshold voltage. Of course, this is the curve obtained in what? Obtained in linear scale. Your x-axis and y-axis are written in the linear scale, but here in this case you have to draw other important graphs. Use the same data, but instead of that, just to draw VG and ID. But in this case, ID is in log 10 scale. So, for example, you have drawing tools like Origin or MATLAB. So whatever, you can easily convert from linear scale to log scale. So please take this semi-logarithmic graph, and if we draw this curve, the same quantity with this semi-logarithmic scale, then you will find that this is corresponding to your graphs here. And please try to check the slope of this sub-threshold region. So of course, since this is a double gate, so gate controllability is almost ideal. So you have to have the slope which is quite close to 60 millivolt per decade, the ideal one. So please check it. Yes, this is the first scenario you have to check. And then what will be the next scenario you have to check? So obviously the next one will be so instead of just stop at 1 millivolt, first takes the first takes the drain sweep. So increase your bias, drain bias up to, for example, 1 volt. Wow. So even in this case, you will have a really negligible current because the transistor itself is completely turned off by this zero gate bias. So increase of your drain current will be quite small. But anyway, it's okay. After that, just like before, increase your gate bias up to what? Up to 1 volt. Then finally you will get the current at what? Gate equal to 1 volt and drain equal to 1 volt. So here 1 volt is not a how can I say the fixed value, but this is just a representative value for so-called VDD, the operation voltage. So nowadays actually this voltage is not exactly 1 volt, slightly lower than that, about 0.7 volt, or even these days slightly lower, 0.6 or something like that. But anyway, as this is just a simulation, so you can apply any voltage. So please increase up to 1,1 configuration. Then now you will have this form. Oh, this graph is corresponding to what? Corresponding to your VD equal to 1 millivolt scale. Then when you have this another gate sweep with VD equal to 1 volt, then how does it look like? So in this case you will have slightly increased behavior. So this curve is corresponding to VD equal to 1 volt. Yes, so in this case curve seems to be just shifted to the negative direction, and you can measure the amount of shift here, and this shift is quite important and it has its own name. What is it? Yes, that is dibble. So this is quite an important quantity. So usually we want to minimize this dibble voltage. So dibble is actually the phenomenon, the name of phenomenon. So this behavior is called as dibble, and the amount of voltage shift should be called as dibble voltage. However, sometimes the people quickly say that what is the dibble? How large is the dibble? Then they say that just some millivolt or 0.1 volt or something like that. And dibble should be also have certain information like what is the value for low voltage and what is the value for large voltage. In this case, for example, we have tested 1 millivolt and 1 volt. However, usually this number is quite close to 0, so it's not that not that important. So usually this number is important. And if you test your dibble with, for example, 0.1 volt case, 0.5 volt case, and 1.0 volt case, what will be the difference? Of course, here compared with 1 millivolt drain bias case, this one will show the smallest shift. and this one will show larger shift, and this one will show the largest shift. So say that debris is larger for this voltage and say that this is small. That is meaningless. Actually, we have to normalize this debris quantity by the drain bias applied for our calculation. So usually debris is calculated by something like this: the shift of your sub-threshold behavior. That should be the denominator, and in the numerator you have to introduce your VD value. Obviously you have to introduce VD high minus VD low, like 1 volt and 1 millivolt, but as I told you before, this one is not that important because this is quite close to 0 volt, so no difference in calculation. So we have to define debris in that way. So please evaluate your debris by comparing these two graphs. So you will find something. And yes, we have a long journey for testing your homework problems, and let's go to the final course. So up to now, what we have done is just to first do the voltage sweep. First set the voltage, then let's try to increase your gate curve. Yes, that was done. So usually that situation or that characteristics are called as input characteristics. Why we call it as input characteristics? So when you consider a transistor, usually gate is considered as an input terminal. So that's the reason why we frequently called as an input characteristics. Okay. However, if we go to the case where drain bias is changed, since drain bias or drain volt terminal is considered as an output terminal, so we will call it as output characteristics. So as a next test, please do this way. Now let's go to case like this. First to go to certain gate bias and 0 volt. In this case you don't have to increase drain bias first, and just to change your gate bias. So this will be quite quick. You can, even when you have gate voltage 1 volt, but you will find that that is not that difficult, because since you have applied just 0 volt to your drain, there is no voltage difference between your source and drain. So simply speaking, your system is still at equilibrium case. So although you are solving the drift diffusion model for this system, but you are repeatedly solving another equilibrium cases. So you will find that your simulation will go quite quickly. Okay, great. After you arrive that VG value, so what will be the VG value? So I just recommend you to introduce like this. Of course, 0, 0.1, 0.2, 0.3. So with 0.1 volt step, please increase up to 1.0. Then you will have 11 different cases for your VG values. After that, yes, so just follow the same rule for increasing another terminal voltage, like so. Now drain current is increased up to 1 volt. In this case, instead of Vg as the x-axis, now we have Vd as x-axis, and here we have id. Yes, id is still there. Then you will find the 11 curves corresponding to your id versus Vd curve. So if your device is turned off, for example, certainly we can say that at Vg equal to 0 condition, your device is turned off, so there will be no current conduction. Point 1, maybe. So let's assume that your threshold voltage is around 0.3. Then up to 0.2, you will have almost nothing. And if you go to 0.3, then you will have a slightly increase of your current. And 4, 5, yes, you will have a further increase. You will have such kind of a behavior. Of course, you will find the values. Okay, so I think that although this is the explanation for how can you test the quality of your homework answer, but I wanted to stress that even when you use a commercial TCAD simulator and do your job as not a TCAD developer but a heavy user of a TCAD simulator, you have to follow exactly the same way for your application. So that is a really important step. So sometimes if we ask somebody to perform the device simulation, they just try to do this job or any of other jobs, so of their own interest. Then I just ask them to, what is the threshold voltage of this one? Then they cannot answer, because with this output curve, maybe we can say about 0.3 or 0.2 will be the threshold voltage. No, threshold voltage is really an important quantity, so you should be able to exactly say what is the threshold voltage for certain device. So simply speaking, that you have to strictly follow this way for characterizing your transistors. So that is quite important. So I think that this lesson is not restricted to the simulation or just in our code. This lesson is fundamentally important for you as a semiconductor device engineer. Every device engineer should understand the importance of this procedure. And you can see that if we have to find out one single metric for, how can I say, not single, but if we have to find out certain most important quantity for characterizing a certain system, then we have to consider this one. Yes. So we have to find, for example, there can be similar curves, but we have to always find out I on and I off. We have to find this. Whether this I off is x-axis or I on is x-axis, that doesn't matter. So then what is the desirable direction? We wanted to have large ohm current and small ohm current. So this diagonal direction is for improving the performance. So also, if we draw in a different way, let's do it for the reference. If we use I off and I on, in this case, yes, I on should be increased and I off should be reduced. So the other way around will be the direction for performance improvement. And here, if we have the opposite, for example, lines, which is perpendicular to this improvement direction, so then we think that these points can be achieved by some trade-off between our performance. So it means that, for example, let's stick to this green line. Yes, we are now having the on current x-axis and off current as a y-axis. Then if we move from this point to that point, what does it mean? So we just reduce the performance. Performance simply means that on current, and by the sacrifice of our performance, instead of that we have better leakage characteristics. That is one thing. And the other way around in this direction is that, okay, instead of that I just boost up my device performance. So when it is turned on, it can conduct a lot of current. Wow! However, when we try to turn it off, unfortunately, since this device conducts quite much, so it is not sufficient room for completely turning off the device. So that is the point. So now this movement along in this way is just regarded as a matter of choice. So we have a lot of rooms to make it. So for example, just changing your threshold voltage will give us some knobs to move around this diagonal compound. However, moving from this point to another point here, this is a completely new story. If in order to achieve this one, we first boost up the performance of our transistor. At the same time, we have to keep our leakage current as small as possible. So both characteristics should be improved. Only when you have such kind of thing, then we can have this movement. So what can be such kind of improvement? So for example, mobility engineering that can introduce a certain knob to increase performance. So certainly when we have a higher mobility for our system, electromobility and Hall mobility, yes, now without changing off current much, we can increase the on current. Yes, so once we move, for example, in this way, then by changing our threshold voltage a little, then also we can live with this line. So whether you have the chance to reduce your up current without sacrificing your performance, or if you have a boost up your own current without increasing your up current, any knob can be used to eventually increase both of them. So they can be regarded as a family. Also, they can be regarded as a family. Okay. So now time is up. So please remember that you have to do a lot of calculation. So also you have to implement your Sharp-Etterman scheme for both of electrons and holes, and test your homework with this one. So that will take a considerable amount of time. So please concentrate on. And since your major is actually this subject, so I think that it is not that much to ask you perform this all kinds of this test, because you have a lot of topics should be covered in this semester. Because once again, if you the students are just including some students from just general course, just like a general course, then I will ask you such kind of heavy computation. But all of you are affiliated to my group, so to you this experience is fundamentally important. So please do this homework within time, and even in next Tuesday, although you have a midterm examination, so I will keep the lecture again. So please come to this room next Tuesday. So if we don't, of course, if we have any kind of COVID-19 situation, then the lecture will be switched back to the online one. So I will let you know. But anyway, so let's have your time, sufficient time to do all of this calculation. Okay. So since time is up, I will just wrap up here now. And if you have any question, then please ask me directly. Okay.